The 50% point occurs on when we've basically hashed it 6 times, and a collision occurs. As we go up in size, you can see this percentage of size when the first collision occurs goes down considerably. As we expand it to 512 elements, the first collision occurs when it's filled to 5%. And as you go up in size, when you go to 4,000 elements, the first collision occurred when the array is only 1.8% full. And you can keep going like this. 65,000, this would be 2 to the 16th. You only have to fill 0.5% of that before the first collision occurs. And you can keep going down, and I went all the way to, what would that be, 2 to the 25th, which is 33 million, roughly. And you can see here with 33 million places filled, at 0.02%, we get our first collision. So it's relatively empty, and our first collision occurs relatively quickly, okay? So that is kind of like a simulation to show you that sure enough, it is absolutely correct. Now these are calculation-wise. You can see these are first collisions, is expected to be here, but this goes up and down depending upon, because these are random events. So the first one, we calculated would be in there, and you got it at 7,000. Of course, there's going to be some instances where it's below, like here calculated at 1,200 and we got it at 979. So I compare the calculation versus the actual, and here the actual, it's 50% is 2,400, but we actually got it 856. So, but the calculation does show you that as you go up in size, the possibility of a collision becomes sooner, faster, quicker. Okay, you still have to fill up the portion of the array, but the collision occurs. Okay, so that shows you that they occur almost immediately. So you have to compensate for that. So having said that, somebody tell me, while I go try to grab the chat box here, somebody tell me how we compensate for a collision. If we're trying to put something in an array, how do we compensate that they're trying to occupy 2 positions or more than 1 position at a time? How do we get around that?
We can use multiple hashes.
No, they're always going to be collide. So you're always going to have something collide into the same spot, and it's going to occur really quick. So what do we do?
Chaining?
No, remember, I suggested if we, let's see, I posted this online in our GitHub repository. So let me go to that. Let me go to that file where, not this one. Doggone it. Let's see. If you'll remember, what we do when we do a hash.
Dr. I can't see your screen.
Oh, sorry about that. If I could keep this blasted chat box open, it would be, I wouldn't have to go back and forth on this. Chat, okay. Let me squeegee that down. So, if you'll remember, our hash simply inputs a string, it's hashed, creates an index, we mod it by the size of the array that we want, and then we stick that into the array. There's going to be a bunch of collisions, and we handle that with a linked list.
Oh yeah, we chained them. That's what I meant by chaining.
Oh, that's what you meant by chaining. Okay. Yes. So we simply handle it with a linked list. Now there's other techniques which I don't find satisfying at all. I don't teach them. And that is you can hash if it's filled, then you look so many places over until you find something that's not. And
I don't like that either.
that's what's ridiculous because it's undecided. And if you have a bunch hit the same spot, you'll be searching for I don't know how long to finally find something. So the best thing to do is simply to do an array of linked lists. Okay. So that's the idea behind that. So the expectation is the same as our birthday solution in terms of, if you want an approximation to it, then you can take the hashes to the array size and do a simple probability calculation. We saw how good that was. So if we go back to our little simulation technique, and we go in and try to calculate the maximum that you would see. So in here, I created an array of 33 million in size, and I did it for all powers of 2. And you can see here distributionally how many out of 32 hashing it 32 times. You can see here most of it, quite a bit of it's empty. Some of it has 1, some of it has 2, some of it has 3. No more than 3 though. And then of course you go up to, and as you continue on down, if you had an array of a size of 1,000, about 36% of it is empty, 38 would have only 1 in it, and the others would share all the way down to as many as 6. Okay, so these are the distributions. And as we get larger and larger, like to 8,000, you'll have a depth of no greater than 7. And as you keep going down, you get to like 2 to the 18th, which is what, 262,000. You've got about 36.8% empty, 36.8% having about 1 here. And then 2 would be half of that 36, and then 3 would be 1/6 of it, and 4 would be 1/24 of it. And we can calculate these. And then of course the maximum would be here at 8. So given that you have 262,000, you would only end up having 8 as the max. And as you keep going down, you can see here that with how much is this? This would be 33 million, 2 to the 25th. Again, about 36.8 is empty. 36.8 has about 1. And then half that, 18%, would have 2. A third of that previous one would have 3. A fourth of that would have 4. A fifth of that would have 5. And so it just 6th, 7th, 8th, 9th, 10th. So you get probabilities down here that are very small. As a matter of fact, only 5 have as many as 10. So with 33 million elements, the depth is no deeper than 10. Very shallow, given that the first collision occurs damn near immediately. So, and this is filled with n items. So I just wanted to simulate that for you so that you got the idea that the distribution. So we may have to pop them in a linked list, but they're not going to be too deep. So to find what we want is going to occur very quickly. Okay. Doesn't matter because the depth there's collisions. So if we tried to find something and it happened to be down there at the level of 10, okay, I need to find X, and I got to go through and hash it, and then, okay, it's not there. And then I go to the next one. So it's going to be 10 deep before I actually find the element. Okay. But that's sure in the hell better than a bisection method, because in a bisection method, how long would it take me to find it?
Is it log 2 of n?
What's that?
Log 2 of n?
Yeah, but what's the log 2 of n here?
Oh, 25.
25. Now, by the way, that would be pretty close to the average. This is the maximum. Does everybody understand the difference? The average here would be about 25, and I mean, we'd occasionally get lucky and find it 1, but if it was right in half, okay? But that's rare. Here, 36% of the time is 0, and 36% of the time is 1. Here, most of the time, if we did the average, most of the time would be on the order of 25 to 24. Whereas here, the most we would look down is 10, which is the most here would damn near be the fastest there. Okay. So this is quite a bit faster than a binary search. So now let's go look at the math. So based upon Omar's suggestions, wait. Shazib, what does the 5 mean?
Oh, I think he said it's a typo.
Okay, okay. So based upon Omar's suggestion, instead of seeing things, he doesn't like my handwriting, obviously. So here we.
And I never said that. It's much better than mine.
I'm implying, but we'll set this up.
Okay.
So anyway, because I need a little picture. Well, this really isn't. Yeah, this is kind of a nice little picture. So the problem is with Overleaf, I can't draw as nice of pictures as I can type things out. So anyway,
Yeah.
let us give you an example of how you might utilize this and why it might be important. Let us say on Google, how many server farms on the planet do you think Google has? And then of course, how many servers do you think Google has?
I don't know. I think in the thousands.
So let's see here. How many servers does Google have?
Oh boy.
Okay.
2.5 million
2.5
data centers.
Yeah. And I wonder how many data centers that is in. How many data centers? $21, and they've got 2.5 million
Oh,
servers.
okay.
Okay, which makes sense.
Makes sense. Yeah, now it makes sense.
So they've got, if you look at that, about 100,000 servers in each data center, roughly.
Yeah.
Something like that. And you can imagine how much heat, how much air conditioning, how much electricity this takes. Okay. So let me go back to here. Here's Google. What happens when you Google? Well, a request goes in for a web page. And Google's got to say, well, we've got billions of users, so we've got to send that request to one of our servers to answer the call. Okay. So the question is, how do I do this? Well, they do the same thing you're going to do. Now, they could, if they wanted to, look at the server, send that information back, and determine how busy it is, and then query each of the servers and say, okay, well, this one's not that busy, and go there. But that communication costs time, it costs a bunch of things. It is better to just analyze it the way that I'm about to analyze it, which is, let us say that we just have a server farm, which each of those data centers has 100,000, and I get a request from you. Yes, you. Each one of you in the classroom. That's got to be handed off to a server. So that request comes in, and Google does this. They go, you know, you. They just randomly choose. Okay, so that's what a hash is. They're just going to randomly choose to pop in a server. And you might say, "Ooh, can't the servers, you know, build up too many requests?" And you're going, "No, because it's a distribution that we just looked at. In other words, I simulated it. So if they were getting 333 million requests, okay, and they only had, you know, server farms like this, we just predicted what the depth would be. Okay, the depth that you would see there, if you saw that, was no more than 10, and each server can handle, 1,000 requests. So this isn't going to be a problem. So we need to analyze this. So anyway, we're going to start with, we have an array. Each one of these looks like a server. And what I would like to do is calculate what's the maximum load that's going to be on any server. In other words, I'd like to know the K, where K in this means the number of occupants in the same cell. Okay, I would like to be able to come out and estimate that. Okay, what that is. That's what I would like to do. So, I can either estimate the probability that it's less than the maximum number, or I could probably estimate the probability that's greater than or equal to the maximum number. So I could take the probability, I'm going to calculate the probability. Okay, I'm going to calculate what Google has done. Actually, you don't have to calculate, we just simulated it. But it gives people a nice warm feeling in their souls if they can match simulation to theory. Just as a little side note, I'll tell you something. The only reason why I have my PhD in statistics is because as an engineer, I simulated everything. You name it, I was a simulation guru. Okay. My simulations, actually, I had to prove that they matched real life. Okay. Unlike the global climate models and everything, they don't have to actually model real life. They just fake stuff and you guys all believe it. But mine actually we actually created algorithms to control things off of. So it had to match things damn near exactly. Okay. So, however, I only had engineering degrees. So I made a proposal to my company that said, "Hey, I think it would be pretty good if we had a PhD in statistics. We can either hire one, or if you'll pay me to go to school, I'll go get mine." Match things exactly after setting sine x equals x. That's pretty good. Well, it actually, for small angles, that's true. So Ash basically, put up a little something there. So anyway, what was interesting is I expected them, the reason why I put this proposal forward was because I wanted to hire a statistician in the group to help. I always want, in case the simulation is wrong, I want some theory to back. In other words, I want to confirm both. I don't want to just do one. I want to confirm both. Now, when I have actual reality to compare it against, then I'm feeling pretty good. But I really like reality, theory, and simulation all match. That's my goal in life, to make sure that those three always come together, because then you thoroughly understand a problem. So anyway, you'll be glad to know that the company accepted my proposal, and they said, "No, we prefer you going and getting your PhD, and we'll pay for it." So that's good. So anyway, once I got accepted, General Dynamics sold the General Dynamics division, Pomona division, to and Rancho Cucamonga division to Hughes, and Hughes moved us. So right when I was doing my PhD, so I had to pay for my PhD. So anyway, that's a funny story. to this day, it just hilarious. But this is a problem that we can go away and look at and see if we can get theory to match simulation. So, and again, the reason why you want to do this is if you can theoretically prove something, maybe then you can extend that to problems that you wouldn't think that you needed to. So I took Omer's advice here and I popped things into overleaf. So let us look at overleaf here. And so if you'll remember, what I'm trying to do is calculate a probability. So if we go back to this little picture, you know, in terms of matching servers, hashing, and these servers can handle more than one job. Typically, they could handle pretty close to 1,000 per. So what I want to do is calculate the probability. So I can either calculate the probability that each server is less than some maximum, or you can calculate the probability that it's greater than or equal to some maximum. So and this one's easier to calculate, so that's the one I'm going to choose to do. So if I go back to overleaf, what I want to do is calculate the probability that all my servers in this case are less than that maximum that I don't want to hit. So another way to look at this is all servers. So what I want to do is find the union of all of these, each individual server in the data center. So this would be like equivalent to the data center, any server in the data center being less than or equal to k. And so what I'm going to do is that's equal to, if I unionize all and each and every server, okay? So this is what I've got to go away and calculate. So, but it's easier for me to calculate the maximum and anything beyond the maximum, so I simply switch it. So I'm looking for the complement. This is the complement of this, okay? So I'm going to utilize the complement, okay? And then I'm going to use a very famous property, the upper bound for the unions here.
Yeah.
And the upper bound for the union is if I just sum all the probabilities. And the reason why is I'll go and show you that, so let me take this little guy here.
Because of overlap. Yeah.
Yeah, matter of fact here. In other words, the union of AB is equal to the addition of A and B, but you subtract off the intersection.
Mhm.
Or like right here, the union of ABC is, you got to subtract off the intersections and add on the center point there for 3 pieces. And of course, this would be the same as the probability, because all the unions, all this is just to divide by the sample space, right? So this would be PA plus PB minus PA intersect B. Okay. So now what I'm going to do though is I'm just going to say, okay, I'm going to have the upper bound. The upper bound is, we know that if I don't consider this, if I just consider these two, this has to be less than or equal to the union. So basically, the probability of union of everything in A has to be less than or equal to the sum of all the probabilities of AI. Okay. Why? Because I'm not subtracting off any of the intersections. So back to my little derivation here. So what I'm saying is, what I'm doing is I'm putting a bound on everything, okay? I'm using inequalities. And you might say, well, Dr. Lair, why are you doing that? Well, you're already doing that. What is the, what's big O?
It's the upper bound.
The upper bound. So what I'm trying to do is find the upper bound. Okay. So I'm using the upper bound here for the union to approximate this. So that's great. There's the sum of I equal 1 to n of all the servers in the database. And I'm going to make sure that I'm going to calculate the maximum out to n. Okay. So now the next step of contention is there. I'm going to try and approximate what that value would be. Okay, an individual one. So I'm going to use another little trick. Just like we did before, finding the probability at the halfway point between the complement and the probability of what I'm trying to determine. I just set the probability equal to a half because I want a measure of what the component would be. So if you look at that, 1/2 here, which I'm going to set the boundary on, the halfway point, is greater than or equal to I equal 1 to n of all those probabilities. And how many of those probabilities are there?
The number of the servers.
N, right?
And yeah.
So n times the individual probability will give me a way to estimate what that probability should be. So 1/2 is less than or equal to n times something. And if you look at the something, well, this has to be 1/2n. So now I've got a bound on the individual component. And if I can keep the individual component to that or less, then I will have met all the conditions. It's just a way of estimating, okay? I'm a pretty good estimator. So I like to estimate things and see how close I get. So now that I have an estimate for an individual server, which is good, what I'm going to do now is I'm going to simply utilize a technique, the Binomial Theorem, to calculate a probability from that, since I want a probability from x of I greater than or equal to k. And if it's binomial, then each spot that I hash into has a probability. And we know what that is because we have n elements in the array. And if you randomly choose one, the probability is going to be 1/n that particular one got chosen. So if I have n positions, I can simply represent the individual probability with just 1/n. So this would be 1/n, and this is q, which is this 1 minus p, which is 1 minus 1/n. So again, this is a binomial approach to calculating the probability. Now I got to use some simplification, just like up here where I estimated what the maximum amount that this could be, okay? In here, what I'm going to do is I'm going to utilize some well-known properties that we've utilized before. And in here, the e to the minus 1/n is simply an estimate of, 1 minus 1/n. So I'm going to pop that right in there. And then we have a bounding condition for the combination, n taken j at a time. So I'm simply going to utilize one of these boundaries. And of course, I want something that's upper bound. So I'm going to choose, now this, you won't find this anywhere. This one you won't find. You'll find these as upper bounds. Binomial coefficient boundary. So you'll typically see the boundaries upper and lower for the binomial coefficient. And if you look at this, just raise to the power k. So you have n divided by k to the k and e times n divided by k to the k. So those are boundaries. And I can derive those for you. And if we had a normal class, I would derive those for you. But I don't like those. I came up with my own. My own is closer because if you, excuse me, if you look down here, this is the lower boundary, the n over k to the k power. This is the binomial coefficient. And then this is the upper boundary, n times e to the divided by k to the k. So, so I want the upper boundary, but I'm going to put an upper boundary that's closer to the actual binomial coefficient. So this is my boundary, okay? N to the j over j factorial. So I'm going to stick this in terms of a bound into there. The reason why is, again, what I'm trying to do is this may be equal to, but I'm trying to get a boundary for this, an upper bound. So what I'm going to do is place these two estimates into the binomial coefficient. So I placed my estimate in there for the binomial coefficient. I placed the estimate for e to the minus 1 over n here into this one. So now I've got some things that I can simplify down. So the n to the j cancels with 1 over n to the j, so I can get rid of that. And then e to the minus n over n, I can pull, that just becomes minus 1, and I can pull that out. So now I've just got the sum of e to the j divided by n over j factorial, okay? So I pull out at k, I pull out e to the k over n over k factorial, I pull that out, and then I take what's left of the sum here, okay? So now we have to sum this term right here. If I can, I have to sum that. So what I do is this. 1/2 is greater than 1 over k plus 1. Here. By the way, these are e to something small. Is just, you know, pretty close to 0. So what's e to the 0?
Just 1.
Just 1. So this is 1 over k plus 1. So I'm going to say that this 1/2 is greater than 1 over k plus 1. And then I'm going to say 1/4 is greater than 1 over k plus 1, k plus 2. Why? Because if 1/2 is this, if you squared this term, that would be 1/4. But this is even less than that because this is not the square. It's k plus 1 over k plus 2. So it's even less than that. And on down the line. So what is the sum of 1 plus 1/2 plus 1/4 plus 1/8 plus all the way out? What is that?
1/2 plus 1/4 plus 1/8.
1 plus 1/2.
It's convergent.
Yeah, converges to what?
Isn't it converged to e?
Converges to 2.
Okay.
Here. So I'm using.
It is 1 over 1 minus c.
I'll just say. Out to infinity.
Yep.
So that's equal to 1 over 2 to the 0 plus 1 over 2 to the first plus 1 over 2 squared plus 1 over 2 cubed all the way down. So what we're basically summing.
1 over n squared. Yeah.
C
1/2.
To 1/2. And we already know the sum of this because we've done this many times. This is a, you know, normally this would be 1 minus c to the
Infinity.
and this 1 minus c, but this c goes to infinity.
It's just 0, so it's 1 over 1/2.
0. So this is equal to 1 over 1 minus 1 over 2. And what's that equal to?
2.
2. So this sum is simply equal to 2. So since that sum is simply equal to 2, and then I have k factorial, and then I just used, if you look at this one, e to the minus 1 over, let me, e to the minus 1 over e to the k to the n, k divided by n. Well, that's also equal to 1 over e to the 1 e to the minus k over n, which is also equal to 1 over e to the 1 minus k over n. And of course, we can approximate this with e to the minus k over n. How's that? In other words, I just used our approximation again in reverse. So, so that's what this would be, e to the minus kn, okay? And of course, if you look at this, that is pretty close to 0. E to the 0 is 1, so we get 1 over e to the 1, okay? And e to the 1 and 2, you know, 2 divided by e to the first, which is 2.7, close to 1. So I'm just going to have it less than or equal to 1 over k factorial. So if you look, we just calculated what the maximum is. And of course, up here, we had 1 over 2 to the n. So 1 over 2 to the n is going to be less than or equal to 1 over k factorial, or k factorial is equal to 2n, or the inverse of factorial. And we can calculate this relatively quickly. Let's go to a spreadsheet. If I want the inverse, I mean, we can use Stirling's approximation, which I do here, to approximate what k factorial is. And you can pop it in, which is fine. Or you can just go to a spreadsheet. And so I'm just going to pop in k. And so let's say it's 1. And so we'll just come down here. I'll go to like 15. And then I'll do k factorial, which is we'll just have this equal to that. And then we'll have this equal to this one times that one. And so then I'll just copy that formula down and we'll have the factorial. So, you know, 5 factorial is, you know, 120 and on down the line. And then, of course, what we got here is we just said that was basically, if we compare 2 times that, so if you look at this, it says that basically if we have an array of size 1440, the depth, in other words, the maximum depth, this is maximum depth, max collisions in any one particular cell should be equivalent to 6, you know, in that area. And if we go down to, what did we have before? 33 million? Where's 33 million? This is 7 million. This is 79 million. So 33 million should be in between here. So the maximum number between 10 and 11. Didn't we get 10? If you
Yes, we did.
We got 10, didn't we?
Yeah, the maximum was 10.
And run this guy. So actually we got, for 33 million in this particular pass, we got 12. So let me,
One time,
yeah, I know.
only once.
Only once. So you got to see how many times it's occurring down here. So here we got 10, it occurred 3 times. So anyway, what you can do is see here, the number of people on Earth is like 8 billion, right? So let's see, where's 8 billion? Maybe I should pop this out in terms of scientific notation so I can actually freaking, I hate looking at, okay, so here is 9 billion. Okay, so we should get on the order of,
No, I think that's 90.
oh, I think you're right. This is 8. This is about, so we should, with 8 billion, should see about, no, that's not 8 billion. It's, we're, a billion is times 10 to the 9th.
Oh, oh yeah. You're absolutely right.
So this would be
Between these
12
two.
billion.
Yeah.
So we should see between 12 and 13 is the depth. Okay. For all the people in the world. In other words, if we like took all the people in the world and wanted to send them an email randomly, just randomly, hash it, send it randomly, nobody would receive any more than 12 emails. Okay. That's every man, woman, and child on the planet. So, so you can see here the depth with the size here of n doesn't go, I mean, it's pretty shallow considering how large these numbers are. With a trillion, 2 trillion, the depth's no more than 15. And of course, if we were doing a binary type search, right, we, 10 to the 12th is roughly equal to 40, 2 to the 40th. So the difference is that would be the maximum. On the other side, the average would be around 40. So it's much faster to hash. So if we go back to our little paper here, and of course, if you want to use Stirling's approximation, then, but you still won't be able to solve it in terms of, in other words, there's no function that you can put into. All you can do is do a calculation and line them up, right? So okay, now in terms of distribution, look at the distribution here. In other words, we already calculated this when I pulled this number out. E to the minus 1, this is about 1. So e to the minus 1 over j factorial would be the approximate distribution. So if we go back to here and look at this, this says, like for 0, hashing to 0 would be e to the minus 1 over 0 factorial. So somebody tell me what e to the minus 1 is.
It's 1 over 3, close to 1 over 3.
Well,
1/4.
got a calculator? Somebody tell me what it should be.
1 over e. 1 over e. Okay.
Yeah.
1 over 2.7. So you know what? Let me calculate that. 1 over e. 0.367879. So very close to 1/3, I would say.
Let's see. What's that?
Very close to 1/3.
In other words, 0.3679.
That is exactly 1 over e.
Yeah. So now let's go and look at e to the minus 1 over 1 factorial. Let's see when it looks equal to 1. Well, that's the same number, isn't it?
Same thing, yeah.
Well, doggone it. It's right on the edge. So aren't these two the same? 0 and 1?
Mm-hmm.
That means about 36.8% won't have anything in it. 36.8% will have 1. element in it. And then now for 2, 2 is 18.38. How do we get 2? Well, let's go back to
2 factorial, so that's
this.
gonna
And that's e to the minus 1 over 2, right? So it should be half. The previous one is 36.79 or 36.8, half that. What do you get?
very close. 18.39.
Yeah. So then we go to the next one, which is 3 collisions. So we would divide by 3 factorial. So it would be 1/6 of this one, right? So 36.8, 1/6 of that, about
Very close.
6.2.
Mhm.
And then of course here we go to the next one, which would be 4 factorial or 24. So this divided by 24 gives us what? 1.5, whatever. So you can
Yeah.
see there's the distribution. So it truly is, there's the distribution for our, it's a binomial distribution is what, what it is. It's what it is. Okay. With that as being our, with the equality, and then we could just sum that up if we wanted to less than or equal to something. So now the next one. Now these are a little hard for people to understand, because what I'm going to do is take the expectation. Now the expectation would just be x times that distribution. And here's the problem with that. It's going to say, what's 0 times anything?
0.
True, but that's not
The case here.
because we actually have to there and go and inspect it. We either have to inspect it with the value or inspect it with the size of what's there. So we're actually going to have to go there and inspect it, even though, because when we hash something, like if we want to find it, just like in our Bloom filter, we would hash it and not know whether it's there or not, right?
Mhm.
So if it's something that we hash that we know that's not there, it's an empty cell, we would still have to investigate that empty cell. So it's not a 0 that we should be multiplying, it's a 1. So if you do that, which is interesting, if you happen to hash an empty, in other words, something that's not there, you would, on the average, find that in 1.36 looks, okay? What's weird is that if it's there, it takes longer to find. So this would be the hash if it's not in there. You'd find it faster than if it is in there. It takes more. So there's a boundary here, both upper and lower, with respect to the average number it takes to get to the one that you want. So when you did an index on an array, that would take you directly there. But when you use this hashing technique, there's going to be a bunch that you may have to look through. So it's going to be greater than 1. Okay. So it falls between if it's there versus if it's not there versus there. The average falls in between. But you know what doesn't matter? What is this not a function of?
It's not a function of time?
No, it's not a function of how big.
Oh, yeah, it's not a function of how big. Yeah, it's not big O of n.
It's just a 1.
Constant. Yeah.
Now, the maximum is logarithmic in nature, kind of like a log-log. In other words, if you're going to calculate what the maximum would be, it would be like a log-log n. But in terms of the average is order 1. Because you can see how, I mean, this is a trillion. If you were to take the log of that, matter of fact, what is the, oops, equal log. It's a little bigger than log. Because if we did Actually, maybe I should be using
Natural log.
maybe the natural log. Maybe here it's natural log, not ln. In our library, it's even then it's the log is it's
Log
bigger than
base
the
2.
log, but less than the obviously the log. So it's less than the log, but bigger than the log. So because the 15 here is twice. And let's see all this. So this would be the ln. Anyway, 2, 3, 5, you know, it's not 9, it grows a little bigger. See that?
Mm-hmm.
It's this log growth is a little larger than K is growing. Okay, so yeah, well, enough of that. So anyway, that is all I got to say about hashing, but was afraid to ask. Okay, so Ansh wants me to do it with
Log base 2.
well, you got to remember with respect to orders, it doesn't matter the base. Big O doesn't matter. Okay, they all. That's not what you equate. You put a C in front of it and do your thing, and basically it doesn't matter what log. So yeah, the derivative, exactly. The derivative is off by a constant. You got it. So anyway, word of the day. What should the word of the day be?
Rewatch, because I will definitely have to rewatch this video, like the recording of the lecture.
2 is you've got your midterm. When did I have it? When did I set it being due?
Monday, I believe.
Nobody's asked any questions but you, Omar. And I opened up some homework for you. By the way, the reason why I opened that homework is to kind of guide you in terms of being able to answer some questions on the midterm. That's why I got that homework there. If you solve those homeworks, you might be able to apply it to your midterm. Okay.
Interesting. For me, it was the opposite. I used the midterm to answer some of
That's
those.
because you did the midterm first.
Yeah.
Not all of you have solved those problems, but I'm trying to give you yeah, either way is fine. So what did we say the word of the day was?
I think rewatch, because I think, so other students should rewatch the recording to fully understand.
We look some things on. Let's use Sterling's approximation.
Binomial, sorry, Sterling?
Or how about the binomial coefficient?
Upper bound?
Upper bound, yeah.
Okay. Binomial coefficient upper bound. Definitely.
Ezekiel brought something up. Will the project be, when's the drop date?
I don't know.
See, you want, okay, I should be able to grade the project by, I'll start taking a peek at it tonight. Okay. So, sounds good. I'll take a peek at those. Most of you did pretty well on those because I've sneak peeked through them. So I'll do that. So anyway, so binomial
coefficient upper bound.
Coefficient upper bound, good. And we'll see all of you
on Monday.
Sounds good. Have a good one.
Bye-bye, Dr. Lair.
Bye-bye.